Greetings, math friends. I'm going to do a two-part series on reasoning that's used in mathematical proofs. There's two basic divisions here that we use when doing proofs in mathematics. So the first thing that we want to look at is kind of basic ideas of what the difference between these two things are. Alright, so I have a couple notes up here for us. On induction, we are drawing a conclusion from a pattern of true examples. On deduction, we are drawing a conclusion from a chain of true statements. So this is typically what you see in your high school geometry classroom. You may see an example of this at some point, but most of the time these classes typically have a lot of deductive reasoning in them. We are going to start with looking at a proof of the sum of the kth rows of Pascal's triangle. Here's the statement of what we want to prove. We're going to prove that the sum of the kth row of Pascal's triangle is 2 to the k power. I have drawn over here Pascal's triangle. This continues on. And I've also labeled the convention we're using for labeling the rows. We're going to count rows starting with 0. So this very top row is row 0, row 1, row 2, and so on. So in row 0, the sum of the terms is 1. There's only 1 there. In row 1, the sum of the terms is 2, and so on. So we're going to try to prove this statement here. To begin this, I'm going to restate it in more of a symbolic form. So I'm going to do the sum from 0 to k, and I'm going to use a vertical combination notation. So I'm going to rewrite this like this. Now we can start to build our pattern of true examples. So I have something to work with here. I have kind of a formula. So I'm going to do case 0. Case 0 is looking at row 0 over here. When we plug things in, we should eventually get a 1 back. So if we look at the left-hand side here, I'm replacing all the k's with zeros. So I'm going to do the sum from 0 to 0. And I'm going to have, that's running from I to k. And so that's going to tell me that I'm going to replace I and k in this bracket by 0 and 0. Here is a formula that allows you to unravel this. And that's going to be that you're going to have k factorial, k minus I factorial times I factorial. That's the formula that we use to break this down. So I'm going to replace all my variables here by 0. So I have 0 factorial, 0 minus 0 is 0 factorial, and 0 factorial. Now something you may or may not remember if you've done this before is that 0 factorial is defined as 1. So this is going to be 1 over 1, which equals 1. So that means that the left-hand side is equal to 1, which is what we were looking for. Now, on the right-hand side, we're going to replace the k with a 0. So if you replace k with 0, we're looking at 2 to the 0 power. From algebra, that this is defined as 1. And so we have 1 on the right-hand side. Also, we have the left-hand side and the right-hand side equaling 1. So we have that case 0 is true. Alright, so we're going to look at case 1 now. So we're counting from 0 to 1. And then we're replacing our I and our k according to the convention here. So I is going to change, that's our index, from 0 to 1. So we have 0 and 1 here. The k term is a constant, so it's going to remain the same up here. And that is associated with the row that we're looking at. So if we do our calculations here, if you run it through the formula, you'll find that this first term is equal to 1. And then if you do the second term also, you will find that that is equal to 1. So we're looking at 1 plus 1 is 2. And then we have to go up here and plug in for k, the number 1. So we're looking at 2 to the first power. And so we have 2 equals 2. So again, we have a true statement here. All right, the next thing that we are going to look at is we're going to assume that k is equal to n, where n is any counting number. And so we're going to count essentially from 0 up to infinity. However, whatever number you want to choose. We're not choosing fractions and decimals here. We're just 0, 1, 2, 3, 4, 5. And so if we plug in n here, we're going to count from 0 to n, wherever n is that you choose. And so we're going to get this sequence of terms that we're adding up. And that has to equal 2 to the n power because we're replacing this k with the n. And so we're going to assume this true. And then this is where the induction really gets serious, is we're going to go ahead and let k equal n plus 1, the next number in the sequence after this one, which we've assumed is true. And then we're going to argue that this is true also. And so if we can arbitrarily pick any term here after 0, and the successive number is always going to be true, then the previous ones should be true as well. I've reset the board a little bit for us. I've added this theorem here that we're going to need to use as a part of this proof. I'm going to leave down in the description a reference for a number theory textbook. This theorem's in that textbook in a very similar form. The variables are different, but it's essentially the same theorem. We are looking at this, and I'm expanding the left-hand side here, and we eventually want to algebraically determine that this left-hand side is in fact this right-hand side. So if you look at the way this theorem looks, this n plus 1 over I is pretty much the form that most of these terms take from the left-hand side that I've written up here. This one looks a little different. But the rest of these look very much like this. And so I'm going to use this kind of in reverse. By the symmetric property of equality, I'm going to look at moving from here to here, since all of my terms here except for one look like this term. Now there's one thing that I can't do, is if you notice over here I have a 0 down here. If I try to apply this here, I'm going to get 0 minus 1 with this term. And so that's going to leave me a negative number. That's undefined, so I can't actually use this theorem here because it's going to throw some things off. We can work around that. We're just going to recopy this first term here exactly as it is. And I'm going to look at the second term, and we're going to see how this theorem applies. So I'm going to apply the theorem to this term. So I'm looking at, I have n plus 1 over some number. And so I can break that down into two terms. The term that I'm adding to 1 and the bottom number go here. So I'm looking at the number I'm adding to 1 and the bottom number. So I'm looking at n1 here, and that's going to be added to the same number again. And whatever the bottom number is, minus 1. So I have 1 minus 1 will give me 0 here. And so this term here is now these two terms here. And then I'm going to do that breakdown across the board until I get to this term. And then again, this term doesn't quite look like this one, but we'll talk about that when we get there. This last one. we have the form here and not quite here, but if I is just a number, this was a natural number, so it's a counting number, so I've added 1. So if you take any counting number, say 5, and you add 1, you get another counting number back. It's closed that way, so that this is just a number 2. So this theorem will apply here. So my top number, I'm going to get n. My bottom number is going to be n plus 1. If we're looking at this pattern, we have the top number here, take the 1 off, is there, and then whatever's in the bottom, we're just copying. So that's what I have here. And then the second term, I have this top number again, and then whatever the bottom number is, I'm subtracting 1. So I have n plus 1 minus 1 just gives me n back. And so I have that. So this is the next step. So now I want to look for a pattern. And so one thing that I want to recognize as a pattern is that I have a sequence in here. And this sequence is counting from 0 to n. This was what we had assumed was true. So we have that term hidden in here. We also have another sequence. We have this sequence. This second sequence we have is very much like the first one, only we are missing the first term where we have a 0. So it's this exact same thing that we're adding in here. But we're missing a term. We're missing the 0 term here. And the n over 0, that was just the number 1 when you calculated it. So we're taking this quantity and we're minusing 1 from it. All right, so we have this same thing twice, but this one's 1 less. Now we have to look at some terms. So we had this term in here that we couldn't do anything with. And then we have another extra term down here that we couldn't do anything with. All right, so now, if you notice the pattern in what we were doing before, whenever we had a number and a 0 here, this was always equal to 1. These two terms, these two summations here are worth 2 to the n power each. We have to subtract 1, and then we have to deal with this term. You will find that this term here is 0. So this one and this one, we have 1 minus 1 is 0. This is a 0. So the only thing that we end up caring about is we have 2 to the n's. All right, so we have 2 to the n's we're adding together. Well, if we have a number plus a number, that's the same as saying 2 times that number. This is equal to 2 to the first power times 2 to the n. And through exponent rules, we know that this is equal to 2 to the base number 2 to the exponents added together. So this is equal to 2 plus 1. So this was the sum of the left-hand side. And over here, this is what we were looking at, trying to prove. This is our expected outcome. This was our sum. So we have indeed proved that through the principle of mathematical induction that this is true. Cheerful calculations.